Hello. In this video, I want to try to resolve the different connotations that the word polar has in chemistry. But rest assured, whether you are talking to an inorganic chemist applying the concepts of general chemistry or talking to an organic chemist, the word polar has the same definition. It's just that in organic chemistry, especially in the laboratory, polarity is often attributed to water solubility. And that is something that's not really emphasized in general chemistry. Now, take a look at these anthropomorphic molecules, molecules that have the shape of humans. They're all made of carbons and hydrogens, and those carbon-hydrogen bonds are not polar. We can consider them nonpolar, and hence the molecule itself, regardless of the shape, is nonpolar. Now, that suffices for general chemistry, but in organic chemistry, we take that one step further and conclude or propose that these molecules are not water soluble. Now, before we move on, I just have to give credit to the Tor group at Rice University. They developed these nanoputions, and they developed some really interesting synthetic chemistry based on these. But let's go back to polarity and water solubility and discuss why that is important. Okay, we are still in Unit 1, alkanes and their conformations. And first of all, I want to remind you, or let's go back in the time machine and talk about these two molecules. Let's see, and let's put this as a chlorine. And in organic chemistry, we are going to be still concerned about shape. And let me explain what these symbols mean. A wedge means that the atom's coming towards you, and the dash means the atom's going away from you. Chlorine in this case is red, and when you have a model, do you see how this hydrogen is towards you? And this hydrogen in the back is going away from you. Now, chlorine is a pretty electronegative atom, and you have a dipole. And that dipole, if you recall from general chemistry, is in this direction, or you could draw a dipole arrow like this. So that pink arrow is called a bond dipole. In general chemistry, this is considered polar. It's also considered polar in organic chemistry, but we're going to see that we're not super concerned about actual polarity. We're more concerned about water solubility, and we'll explain why in just a bit. So this molecule is CH3Cl. Now, if I have all those bonds to chlorine, then you'll recall that those dipoles cancel out. So you'll have a net dipole of 0, or 0 net. Instead of a bond dipole, now we're looking at the molecular dipole. So there are two types of dipoles that you learn in general chemistry, a bond dipole versus a molecular dipole. And that molecule is here. And yeah, if the chlorine is pulling in all four directions, then the molecule is, I like to think of it as tug of war. And you have four people pulling towards the chlorines. That central atom is not going to move. We consider that nonpolar because the bond dipoles cancel out. Now the issue comes when we go into the organic chemistry lab, because in organic, the phrase that people always repeat to themselves because it's so important is, let me just write this down, like dissolves like. And that's where it's a little bit conflicty, or that's not a word, but there's a conflict when you try to apply this, like dissolves like, to these two molecules. Because you all know that water, H2O, is definitely polar. Okay, we have a very strong dipole towards the oxygen. If you want to test yourself, the net dipole is going straight up when you combine the two bond dipoles. The thing is, if like dissolves like, water is a very common solvent in organic chemistry. Water, though, would or cannot dissolve either of these, even though this molecule is polar. So not only do we understand that this is polar and nonpolar based on the bond dipoles either canceling out or not, now in organic chemistry we are concerned about water solubility. So both of these, both CH3Cl and CCl4 are not water soluble, or you could say are water insoluble. Okay, this is going to be helpful, you'll see in lab, because there's a glassware called separatory funnel. Separatory funnel looks like this, and it has a spout at the bottom that you could drain. The thing is, when you have water and either these two solvents, chlorinated solvents, your chlorinated solvents will separate from the water, almost like oil and vinegar. So no matter if it's CH3Cl or CCl4, we'll just call this chlorinated solvents. That's going to be separate from, I'll use blue, separate from the water layer. Okay, and the thing is, if you could run a reaction in which your product is water soluble and your impurities are chlorinated solvent soluble, or you could even think of it as organic soluble, then you could have a good purification. Okay. So in practice, how do we figure out polarity and water solubility? Well, there's a couple things. The first is that you will get a feel for what is water soluble and what is organic soluble. Versus organic. And we'll have time to look at some solvents that are water-based versus organic-based. In general, polar molecules are going to be water-soluble, and nonpolar molecules are going to be organic-soluble, but we're not going to be depending on geometry like we did in general chemistry. We're going to be depending on the number of bond dipoles that a molecule has compared to carbon-hydrogen bonds. Okay, so the first thing is one, if there are a lot of atoms that are not carbon and hydrogen. So looking at the periodic table, if there's a lot of nitrogen, oxygen, fluorine, and the halogens, chlorine, bromine, and iodine, relative to number of carbon and hydrogens, then the molecule will likely be polar. So if there's a lot of NOF, and then going down the halogen group, Cl, Br, I, compared to C and H, then it's likely polar and thus has a good chance to be water soluble. Remember, like dissolves like. Even though we saw an example where it doesn't work. Okay, I wanted to show you the conflict here because water can not dissolve either of these two solvents. They are what's called immiscible. Okay, just jot down that word also, immiscible. Immiscible. Okay, so that's number one, and we should have time to look at some examples. Number two, if a molecule is charged, has a plus charge or a minus charge or multiple charges, then it's likely, again, polar. the whole molecule itself, not just a certain section. And oops, we should say water soluble here. And then if it's polar, for the most part, we're going to say it's water soluble. Now again, there are exceptions. Okay. Now let me just jot down here some bonds that are polar, because the more bonds of these you have, the more polar your molecule is. More polar the molecule. Let's do CN, CO single bond. A CO double bond is a very polar bond. The double bond between carbon and oxygen. And then also you have your halogens, CF, CBr, CCl. Okay. If you have a lot of those types of bonds in your molecule, then it is likely that your molecule is polar. But if there's a lot of carbon-hydrogen bonds and only carbon-hydrogen bonds, or only carbon-carbon bonds, then your molecule is nonpolar and likely insoluble. And we have that case again with these am I saying that right? Anthropomorphic molecules. Okay. What I want to do next is to find another piece of paper and give you some lab solvents. Solvents that you need to be, or you will naturally become accustomed to working with. Because if you could figure out what solvents can solubilize your compounds, then you have a good chance of figuring out a purification technique. So polarity is important. Two main reasons. Before we talk about purification, the first reason is reactions work better, or you could even say faster, if starting materials or starting reactants are soluble. They mix. Okay. Reactions, what's going on with my handwriting? Reactions work better and faster if the starting reactants are soluble, that they mix well and they're dissolved. If you have just chunks of solid that sits at the bottom of the round bottom flask, your reaction's not going to work very well. So based on your starting material, the structure, then you want to decide, do I want a polar solvent or do I want a non-polar solvent? And then the second one is purification is easy if, for instance, the impurities are, let's say, water soluble, but your product is, we'll call it organic soluble. And we'll give you some examples right now. Okay, so we're looking at different solvents. All right, common lab solvents. And from the structure, let's decide or predict whether they are going to be water or aqueous or organic. And then once you have that, you can decide what kind of molecules they will dissolve. The first one is hexane. Okay. Hexane is very nonpolar. And nonpolar solvents dissolve nonpolar molecules. Molecules that don't have a lot of these atoms. Molecules that are not charged, right? Because these are two examples where we have something polar, but nonpolar solvents dissolve nonpolar molecules, so we're looking for the opposite. Okay, so hexane is an example of an organic solvent. It dissolves organic nonpolar molecules. Let's do water. Water is obviously polar, and it dissolves polar solvent, and it dissolves polar molecules. Okay. What about acetone? Acetone, I'm going to use a combination of, no, I'll use sort of a Lewis structure. This is acetone. Acetone can dissolve both because it has characteristics of both. So acetone is a very cool solvent because it can dissolve almost anything. It can dissolve polar and nonpolar molecules. Again, acetone is a good reaction solvent because everything is soluble in it, although there's a caveat. You don't want your product to be soluble because then you wouldn't be able to separate the starting material from the product. So there's a little warning if you use acetone as a reaction solvent. But another thing that you'll see acetone used for is it cleans everything. Because if you have dirty glassware, whether that glassware has polar molecules stuck to it or nonpolar molecules, acetone can typically wash that away. Okay. Now let me show you an example of some tricks in organic chemistry where you can make a molecule that is organic soluble into a molecule that's water soluble. And the one trick is this. This is, what is this? This is methyl salicylate. Okay. Let me just double check. I think this is wintergreen oil. Wintergreen oil. This, I know it has a bunch of oxygens, but actually this is not water soluble. It's almost water soluble, but it's not quite. Okay, so it can dissolve in organic solvents. Dissolves in stuff like CHCl3, maybe hexane, maybe. A lot of this is trial and error. Okay, but the thing is, if you add a strong base, let's add NaOH. What you could do, I know at this point you haven't gone through acid and bases in organic chemistry, but you have done a little bit of acid base in general chemistry. You get what's called a proton transfer. And this is our first molecule in this video where we're going to get something that's charged. This is O minus. Now it's O minus because you have an oxygen with one bond and 3 lone pairs. We're not going to go over the details why that's true. That's for another video. And what else do we have? We have water because the H was transferred, and actually form a salt. Okay, everything is balanced actually in this reaction now. Charged molecules. That was the second point here. If a molecule is charged, then it is likely polar and water soluble. To get methyl salicylate to be water soluble, you have to add base to make it charged. So now that it is, what color do I want to use? Charged, has a minus charge. Okay, right there. Okay, don't worry that it's paired up with this plus. You consider the organic part of the molecule negatively charged. Then it is water soluble. It is, we could say polar, or polar enough to be water soluble. Look at the difference between our original methyl salicylate and the methyl salicylate it's called deprotonated because we remove a hydrogen, but we only remove the proton actually. The electrons are left behind. So we remove what's called a proton, or you could say deprotonated. This is not water soluble, and this is water soluble. Okay. Why would you want to use that trick? Because what if methyl salicylate is actually an impurity, but your product is also not water soluble? So your product and this impurity are all dissolved in the same solvent, a nonpolar solvent, right? These are nonpolar. See, I want to be careful. Technically, that molecule doesn't cancel out all its bond dipoles. But again, see, the organic chemistry in me is coming out because I consider it nonpolar because it's not soluble in water, even though this molecule right here is actually polar according to general chemistry. So, man, we'll just call these organic solvents. How about that? Okay, and this is an aqueous solvent. But the aqueous solvent has to be basic for this to happen. So get it into your heads as you walk into an organic chemistry lab that charged molecules are almost always going to be water soluble. And that's going to be that's going to be the trick in terms of purifying something that's charged versus uncharged by using different types of water. Here we have basic water, all right? NaOH in water, or you could say NaOH using this notation, aqueous. Let me show you the opposite. Here we made it negatively charged. Let me show you something that's positively charged. I'm going to draw a molecule, and we're going to discuss whether we think it's water soluble or not. Okay. Dimethyl is called dimethylaniline. It does have a nitrogen, and we said that if it has nitrogen, it might be water soluble, but relative to all the carbons and hydrogens, which is actually a nonpolar bond, right? CH bonds are going to be considered nonpolar. Then, that's not enough dipole, that's not enough polarity to make the whole molecule polar. So this is actually nonpolar. And what kind of solvent does it dissolve in? Organic solvent. Hexanes, chloroform, which is CHCl3. No, sorry. Yeah, CHCl3. Acetone will dissolve this. Organic solvent, soluble. This actually is what's called basic. And again, you'll get into acid bases a bit later, but hopefully some of your general chemistry acid base knowledge has stuck around because now that nitrogen will accept this proton. And what happens here, if you know your formal charge rules, that nitrogen doesn't have a lone pair now. It has a hydrogen bond or a bond to hydrogen. This is actually positive. Your Cl hangs out with a positive plus, oh, no, that's it. Everything is together. But the big difference is that now this is charged. So again, the colors actually, I'm mixing up the colors all over the place, but this is charged, and hence, what are you going to say? This is polar, and like dissolves like, therefore this is water soluble now. Okay, water soluble. There are numerous examples of this in pharmaceuticals. If you look at your pharmaceuticals, if something needs to be orally viable, it needs to be able to dissolve in your tummy. And your tummy is an acidic aqueous environment. Well, drugs that have this nitrogen will become protonated and will become soluble, which is good because it can be absorbed readily into your bloodstream. You don't want a drug that's water insoluble because it will do nothing. Just like we said here that if you have a reaction where it's not soluble, then it won't work. You want things to be soluble so they can mix better. All right, I know that was a lot, and It's a little bit abstract because we don't have the chemicals in front of us and the solvents, but you'll see as you do some of these labs in Organic Chemistry 1 and 2 that solubility is going to be super important, and your ability to predict whether a molecule, whether it's a product or side product or impurity, is water soluble or not, that will help you decide the course of how the reaction is going to proceed and how you want to purify once the reaction is complete.